When engineering LLM systems, architects face a strict structural divide. You are either building rigid, hard-coded mechanisms or designing fluid, adapting intelligence. Every architectural decision here is dictated by a single variable, the predictability of the required subtasks. Anthropic defines this divide as a choice between workflows and agents. Workflows follow predefined paths, and agent dynamically directs its own process. This graph models the spectrum between writing rigid instructions and steering open-ended investigations. The left pole is prompt chaining, fixed workflows where paths are pre-calculated. The right pole is dynamic decomposition. The LLM evaluates data to direct its own next steps. Mismatching architecture carries a heavy cost. You invite failure, locking unpredictable tasks into rigid pipelines, or you waste compute by over-engineering a simple linear process. Mastering this predictability access is the difference between deploying a resilient enterprise application and maintaining a brittle, wasteful one. Prompt chaining is the foundational pattern for tasks where every step is knowable and sequenceable. In this model, the architect decomposes the task completely prior to execution. You are writing a rigid recipe for the LLM to follow. This diagram shows a strict sequential pipeline. Each discrete LLM call is isolated, and each subsequent node builds exclusively on the output of the node before it. Because the steps are isolated, we can introduce quality control. We place programmatic gates between the LLM calls. These gates run code-based validations on the intermediate outputs. If an output fails to meet specific accuracy thresholds, the chain halts before the error cascades. This highlights the core trade-off. By forcing the LLM to handle narrower, easier tasks one at a time, you drastically increase the per-step accuracy. That accuracy comes with a penalty. Making multiple sequential API calls introduces significant latency into the system. You accept this latency when handling predictable, multi-aspect work that is relatively low in overall complexity. Prompt chaining deliberately trades execution speed for precision. It ensures the LLM is never overwhelmed by conflicting instructions. Consider a common engineering anti-pattern, attempting to run a comprehensive, multi-file code review with a single massive prompt. This triggers attention dilution. The massive prompt spreads the LLM's attention too thin, fracturing its focus. We fix this by separating the cognitive load, routing each file into an isolated local analysis. Phase 1 is the per-file local analysis. It provides the model with a small, highly focused context window, dedicated exclusively to deep logic checks and style validations on that specific code. But reviewing files in isolation creates a blind spot. Phase 2 requires a completely different type of analytical attention. The outputs flow into a single integration pass to check for architectural drift. This dedicated cross-file step catches the broken call sites and interface mismatches that individual, isolated file reviews cannot see. Local depth and global consistency are distinct attention problems. Hard coding them into isolated sequential steps is the only way to guarantee accuracy for both. We move to the right side of the axis when we encounter complex environments where the required subtasks are completely hidden from us. Here, a central LLM acts as an orchestrator rather than a mere participant. It evaluates the unknown, breaks the task down, delegates distinct parts to specialized workers, and synthesizes the returning data into a final output. Take a directive like adding comprehensive tests to a sprawling legacy codebase. Prompt chaining fails here. It is impossible to write a sequential recipe for code dependencies you have not discovered yet. Instead, the orchestrator begins with a broad mapping phase to survey the existing modules and their interconnectivity. The orchestrator uses this structural map to identify the high-impact, untested, or heavily dependent on areas of the codebase, deciding where to deploy its workers first. When the environment is unknown, the architecture must empower the LLM to steer its own investigation based entirely on its intermediate findings. Based on that initial mapping phase, the orchestrator generates a prioritized plan of attack. Crucially, this plan is a living artifact. The orchestrator constantly adapts and revises its strategy as tangled dependencies and missing seams surface during execution. A critical misconception in system design is mistaking this dynamic decomposition for basic parallel execution. Let's look at a split-screen comparison of their starting conditions. On the left, parallelization simply splits a known, predictable task into equal parts to process uniform data faster. On the right, dynamic decomposition uses the orchestrator to analyze an amorphous problem and discover the constituent parts based on the unique input. Parallelization is merely an execution strategy for known variables. Dynamic orchestrators are discovery engines built to process unknowns. The overarching rule of LLM architecture is to always default to the simplest functional pattern. Architects often fall into the orchestrator trap, wasting compute and degrading system reliability by building complex dynamic agents for jobs a simple chain can handle. We use a selection heuristic framework. At the foundation, prompt chaining handles predictable steps. The middle rung, orchestrator workers, processes unpredictable tasks, relying on intermediate findings. The apex is strictly for multi-agent systems with autonomous, interacting roles. To justify escalating this ladder, architects rely on a definitive, binary test known as the tell. The rule is strict. If the nature of the next subtask depends entirely on the result of the current one, you must use dynamic decomposition. Conversely, if you can map out every required step on a whiteboard before writing a single line of code, lock it into a fixed chain. Masterful AI architecture is a matter of perfectly balancing the predictability of the task with the rigidity of the workflow.